All right, today's lecture is on the properties of the ionic bonds. When you have a compound that is bonded ionically, what properties do we expect from that material? Okay, so this is along the lines been called material science. What are distinct properties that make them based on how they're held together? Now again, the ionic bond is an electrostatic force of attraction, just like Coulombic attraction. There's the cations, like sodium ions, and the chloride ions, which is negative. It's the attraction of the positive and negative, and that is a very strong bond. Okay, ionic bonds are the strongest bonds that we'll study in the next 2 units, and that is it's a very strong bond to break. Now, when sodium chloride or other ionic compounds come together, they create, down here you can see a picture of them, they create different arrangements. And this arrangement of the cations and the anions is called a crystal lattice. A crystal lattice is the 3D arrangement of the particles, and that's dictated mainly by the ratio of ions. For example, sodium chloride is a ratio of 1 to 1. Okay? So you can see here that when sodium chloride comes together, it tends to form a cubic structure. Okay? But then down here, we have this calcium compound, which does not have a ratio of 1 to 1. Okay? And because of that, its arrangement of the ions is different. And here we can see an arrangement that is forming more of a diamond pattern shape to it. Okay? So the charge on the ions and the ratio of the ions will cause there to be different structural arrangement of these positive and negative ions, and that causes a different three-dimensional network. So this is called a crystal lattice. A crystal lattice is the 3D arrangement of the positive and negative ions. Okay? One other note, when we have, for example, water is the chemical formula H2O. One H2O unit is called a molecule. But we use the word molecule to describe chemical compounds that are held together by covalent bonds. We do not use the word molecule to describe an ionic compound. Salt, table salt, is an example of an ionic compound, NaCl. One sodium chloride unit is not called a molecule. Instead, the word that we use to describe it is called a formula unit. So formula unit to an ionic compound is the same thing as molecule is to a covalent compound. It simply means the lowest unit of positive and negative ions that makes one particulate. Okay? That's called a formula unit. All right, lattice energy. Lattice energy is the amount of energy it takes to break an ionic bond. So the higher the lattice energy, the more energy it takes to break the bond. That tells us that it is a stronger bond. So the higher the lattice energy, it takes more energy to break the bond. That tells me that it's a stronger bond. The equation for lattice energy is very similar to Coulombic attraction. When we do Coulombic attraction, in the Pogel activity, the equation was Q1 Q2 over D squared. So you'll notice the only thing that's different is there is no square on the distance. And because of that now, the distance factor is not as big of a factor in lattice energy as it is with Coulombic attraction. Okay? It still is a factor, but it's not as the dominant factor as it was before. All right, so there are 2 factors that affects the amount of lattice energy of an ionic compound. Again, we still have the attraction of the positive ion to the negative ion. What are the 2 factors? It's the same as Coulombic attraction. But the first factor to consider is the charge on the ions. The charge on the ions is the first thing you want to look at when we look at the strength of an ionic bond. Okay, and again, that's because the distance variable is not squared any longer. If the charge on the ions is the same, to break the tie, we then look at the distance. Okay? So the charge on the ions, you'll notice Q1 and Q2. Q1 is the charge on the cation, and Q2 is the charge on the anion. When we multiply them together, this is called the charge product. The higher the charge product, the stronger the bond. So the greater the charge on the ions, the higher the lattice energy. Okay? So an example of that, if I have an ionic compound that has a +1 +1, and a -1. And then I have another ionic compound that has a +2 and the -1. The +2 and -1 has a charge product of 2. This is a charge product of 1. I ignore the negative symbol. So when we have greater charges, the one that I boxed in, this ionic compound would have a greater lattice energy because a +2 ion has got a greater electrical attraction than a +1 ion. Okay? Distance, same relationship as coulombic attraction. The bigger the ions, they can't pack together as closely in the crystal lattice, and that causes a lower lattice energy. So the smaller the ions are, the stronger the bond is, the higher the lattice energy. The only variable you have to consider is going down a family. When you go down a family, atoms get bigger, right? The same thing is true for ions. When you go down a family of ions, their ions also get larger. So whenever you ask the question about size, when we look at being able to separate the strength of ionic bonds, you will be looking at elements in the same family. As you go down, they get bigger and bigger. And the bigger they are, the lower their lattice energy. All right, so based on those two things, I would like you to pause the lecture right now, and I've given you magnesium oxide, potassium iodide, and calcium chloride. Arrange those three ionic compounds in order from the strongest bond, which means they have the highest lattice energy, to the weakest bond, which means they have the lowest lattice energy. So look at charge on the ions, and then look at distance. All right, so I wrote the charges above each of the ionic compounds. Now, if you're wondering, how do I know the charges of the ions? Well, one way is you can look at the periodic table. Magnesium is in group 2, and elements in group 2 will always form a +2 charge. Another way of doing that is on the ions. So magnesium +2 -2, potassium iodide +1 -1, sodium chloride +1 -1. So magnesium oxide has got a charge product of 4, potassium iodide has a charge product of 1, and sodium chloride has a charge product of 1. 2 times 2 is 4, 1 times 1 is 1. Because magnesium oxide has got the greatest charge product, I know that magnesium oxide will have the largest lattice energy. It also has the strongest bond. Now, potassium iodide and sodium chloride have the same charge product. So now I have to look at the second variable, which is size. If I look up potassium and sodium, you'll notice on the periodic table that sodium is above potassium. When we go down, ions get bigger. Chloride and iodide are also in the same family in group 17. Iodide is also below chlorine. It too is bigger. So potassium and iodide ions are both much larger than sodium and chloride. And because of that, potassium iodide ions can't get as close together, and that increased distance weakens the attraction. Therefore, the proper order would be magnesium oxide would have the highest lattice energy and potassium iodide would have the lowest. The more charge and the smaller the ions, the higher the lattice energy, stronger bond. The bigger the ions and the lower the charge, the weaker the lattice energy and the weaker the bond. Okay? This is an example of the Chem Helper. When you look at the Chem Helper, which is the blue laminate sheet that I gave you, now if you're a virtual student, I have given you the Chem Helper as an electronic copy. It's in the very first module. It's the very first tab. If you go back to your modules in the class and look up the Chem Helper, you can print this off. But on one side of the Chem Helper, one side is the periodic table, the other side is this equation sheet. Right in the middle it says chemistry. Right above it there is an ion table. And this ion table gives you the charges of all the ions that we'll have for this unit. Something very important that you want to reference. If you look, every element that's written in the +1 column means those are ions that have a +1 charge. +2, +3, +4, and then it goes -1, -2, -3. When we have an ionic compound, the very first compound is always a positive ion, the second is always a negative ion. So you just have to figure out where the positive and negative parts are separated. Pretty easy when it's only got 2 elements, and then look it up. For example, magnesium was in the +2 column, and oxygen was in the -2 column. So that's how I'm able to look up, use the chem helper to figure out. All right, next page. What are some properties of ionic bonds? Ionic bonds have very high melting points. If you think back to the first lab of the year, powder A in the unknown powders lab was sodium chloride. When you heated it with a Bunsen burner flame for even several minutes, it did nothing. The crystal stayed perfectly intact because sodium chloride has a very high melting point over almost 1,000 degrees Celsius. Boiling points are excessively high. Okay, to boil sodium chloride would take enormous energies. Most labs couldn't even produce that type of energy. Okay, the question becomes, why do they have such high melting points and such high boiling points? Well, to melt something means we got to break the ion apart from the other ions. We have to break the bond. And what do we know about ionic compounds? Ionic compounds have much stronger bonds, okay, than metallic. And both metallic and ionic bonds are significantly stronger than covalent. So compounds that are held together by covalent bonds tend to have very low melting points and boiling points compared to ionic and metallic. But ionic typically, in a generalization, has got extremely strong attractive forces, so it takes a lot of energy to break them to make the compound into a liquid and then even to boil them. All right, next property of ionic compounds, they are conductive. Conductive means that they will carry an electrical current. When we have an ionic compound in a solid form, and again, the solid has alternating positive and negative particles. You'll see, like, for example, this positive particle is surrounded by negatives because it has to be so that there's an electrical attraction. We can't have negatives next to negatives because they would repel and the crystal would not be held together. If I were to connect a wire to a chunk of salt and apply electrical current is nothing more than a flow of negative electrons. The problem with a solid is these positive and negative particles, they can wiggle and vibrate, but that negative particle cannot move. And because the negative particle cannot move, electrical current will not flow to the other end of the crystal. So ionic compounds are not conductive. They are not conductive in the solid state because the particles cannot migrate through the crystal. They are held together by very strong ionic bonds, and those negative charges can't carry throughout the crystal. However, if I were to heat the material and make it a liquid, I know a negative particle now. When things are liquids, their particles can move and migrate throughout the substance. So if I were to put a wire and send electrons into the solution and have another wire out, we would see that electrical current would flow through the liquid because now the particles can move. So since the ions now can move throughout the material, it is conductive. So ionic compounds are conductive in the liquid state, but they are not conductive in the solid state. Okay? Ionic compounds are very hard materials, but they're very brittle. Well, how is that possible? Again, because the ionic compound is held together by such strong bonds, that forms a very hard material. But if I were to take a crystal of it that are, again, alternating positive and negative charges, if I were to tap on it with a hammer, if I were to apply a force to it and cause the crystalline pattern just to shift slightly, okay? And if I were to shift these two layers down one, okay? By shifting it just down one unit, you'll notice that all of a sudden now positive and negatives align with another. So by putting a force to it, by tapping on it, a sharp blow to it, if I just shift the pattern of the arrangement just slightly, now we're going to have repulsion. And that's going to cause the material to separate apart. And that's why these materials are brittle. Okay, if you take a chunk of ionic compound like salt and tap on it with a hammer, I can guarantee you that it will crumble and fall apart into a much smaller chunks and pieces of sodium chloride. Okay, so ionic compounds are hard, but they're very brittle because small minor changes in their alternating positive negative arrangement will cause it to repel and cleave and separate. Lastly, some ionic compounds are soluble in water, but not all. And that's what the lab in this unit is going to focus in on for this cycle. Okay, so here again I have a chunk of sodium chloride, positive, negative. Here's the crystal lattice. Water molecules are said to be polar molecules. What does that mean? It means that it has a positive pole and a negative pole. And this is because water, H2O, oxygen is very electronegative from our last unit. And because it's very electronegative, it has a negative charge associated with it. Hydrogen is much less electronegative and has the positive charge. So water has got a positive pole and a negative pole, which we can see here by these red and white molecules. The red molecules, or red atoms, are oxygen, and the white ones are hydrogen. So you can see that the negative green ions, that the positive hydrogen is much closer to it than the red oxygen. And so the positive part of the water will be attracted to the negative chloride ions, and these ions will attach to this crystal, and they will pull, because water is a fluid and can move, it will pull that ion apart. Okay? And that pulling of the ions apart, what's going to happen is you're going to see that crystal of sodium chloride get smaller and smaller. To your eyes, it looks like the crystal is dissolving. But not only is it dissolving because the water molecules are attracted to it, but the water molecules will surround the particles. Here you can see all of the red oxygen atoms of all the water molecules are attracted to the positive sodium ion because, again, oxygen has got a negative charge. It's the negative end of water. And that surrounding of the water molecules of the ions is called solvation. The more attraction there is of the ions to the water molecules, the more soluble the material. Okay? So that surrounding of the water molecules, and here we can see a negative chloride ion is being surrounded by the white, which is the positive hydrogen atoms. This process is called solvation. So the sodium chloride, when you put the solid sodium chloride into water, it's not reacting with water, but since the water is attaching to the sodium chloride atoms and pulling them apart, this process is called dissociation. The sodium chloride solid is separating into its positive and negative ions. And that process is called dissociation. So ionic compounds that are soluble in water, they dissociate in water, producing ions. If you have a chemical compound that when you put it in water, it develops ions in water, this is said to be an electrolyte. You often hear about electrolytes with like Gatorade or Powerade. Okay? Electrolytes is just a fancy word for things that produce ions in water. In essence, salts. Electrolytes are salts. So when they advertise Gatorade, they're really advertising for saltwater solutions. But it sounds fancy. It sounds like it's a chemical that your body needs. In essence, it's not too hard to make Gatorade solutions. Okay? All right, so lastly, write the dissociation equations for each of the following compounds. So here, you can see the chemical compound KBr, potassium bromide. When you put it into water, what will it separate into? It's going to separate into potassium and bromide, but not atoms. It's going to separate into ions. And potassium is group 1, has got a charge of +1, and bromide has a charge of -1. Okay? All right, let's go ahead and look at calcium chloride. What is it going to break apart into? Now, if you look at calcium chloride, you got a calcium +2 ion, and that 2 underneath of the chlorine means that there are 2 chloride ions. Why does there need to be 2 chloride ions for every calcium ion? Well, that's because when you look up chloride, you'll notice that it has a charge of -1. Well, we need 2 -1s to balance out the +2 from our last lecture. So the 2 there indicates that there's 2 chloride ions. So when this thing dissociates, what does it dissociate into? It's going to produce 1 calcium ion for every ionic compound and 2 chloride ions Okay, so the subscripts become coefficients because of the fact that there's 2 chloride ions for every calcium ions. So calcium chloride will break apart. Every calcium chloride compound will end up producing 3 ions each, 1 calcium ion and 2 chloride ions. And you can get that if you draw the Lewis structure of the chemical compound. All right, go ahead and do the next 2 dissociation equations for the following compounds. All right, so sodium oxide. Again, there's 2 sodiums because if you look up the ion table, sodium has a +1 charge and oxygen has a -2. So we need 2 sodium ions to balance the -2 off of the single oxygen ion. Okay, so when it dissociates, again, the subscripts become coefficients. So sodium oxide is going to break apart into sodium ions and oxide ions. Aluminum nitrate, the weird thing about this is something we haven't talked about much before, and that's called nitrate. This is called a polyatomic ion. A polyatomic ion is a bonded group of atoms that all together they form a single charge. So a nitrogen atom bonds with 3 oxygen atoms, and when they do, they can form the nitrate ion. So the 4 atoms all together have a single -1 charge. This is called a polyatomic ion. It's different than like chloride. Chloride is called a monatomic ion because it contains 1 element, 1 atom of it, monatomic. Nitrate is a polyatomic ion, still has a charge on it, but it's got more than 1 type of element. So each nitrate is -1. Aluminum is a +3 ion. So therefore, you need 3 nitrate groups to surround the aluminum so that the sum of all of the ions will add to 0. So therefore, when this thing dissociates, we're going to get 1 aluminum ion, and we're going to get 3 nitrate ions. And we'll talk more about this next week when we do the POGL activity on naming ionic compounds. And that'll really do a good job of explaining polyatomic ions. But you can see here that this aluminum compound breaks apart into 1 aluminum ion and 3 nitrate ions. So we're getting 4 ions are breaking apart when this molecule separates and dissociates into the chemical compound. So dissociation is just a fancy word for saying when an ionic compound dissolves in water, it breaks apart into ions. And those ions causes water to be electrolytic, which means there's ions floating around in it. Okay, so those are properties of ionic compounds. They have high melting points and high boiling points. They're conductive in the liquid state, but not the solid state. They're hard, but very brittle, and many of them dissolve in water. And our lab for this cycle will look at how we can identify if they are soluble in water or if they're not. Some ionic compounds are soluble in water and some are not. And that depends on the strength of the bond. If the bond is extremely strong, then even water doesn't have the ability to pull it apart and to dissolve it. Okay? Thanks again for listening, and next week we'll look at metallic bonds.